It says March Madness. Have you guys been watching this weekend? Anyone watch March Madness? Nobody?
You watched March Madness?
I did. Not good, to be honest. I still have Duke, but barely.
But who
Duke, North Carolina. I forget the other two.
It's probably Tennessee or UVA or K-State.
So March Madness is an example of an exponential decay function modeled by, and this is the equation that models that, and it's very similar to our M&M experiment. So this is the equation. What do you think the 64 represents? Yeah, the beginning amount, how many teams began. And then what do you think the B value represents? Yeah, the rate that they are growing or decaying. In this case, half and half and half and half, what's happening? It's decay, good. Raised to the x times or x rounds, okay? So you can see here, if x is 0, how many games have been played? 0 games have been played, so we have 64 teams selected into the tournament, right? Okay, after one round, so x is 1, after one turn, how many teams are left? 32. The 32 teams. So only, see how fast that went down? Yeah. Literally, every team's played only one game, and we already have half as many teams left. Just like that, 32, okay? After the second round, so now x becomes 2, how many teams are left? 16. Yeah, Sweet 16, that starts, what, Thursday or Friday, I think? And then after 3 rounds, we're down to the Elite 8, and then the Final 4, the championship game, and then after 6 rounds, the champion. So how many rounds did it take to turn 64 into 1? Yeah, it happens really fast. That's our exponential decay. Okay. So what we're going to do today, I'm really not even going to do much of this stuff up here. For the sake of time, we're going to mostly use our calculators to graph for exponentials, okay? So go ahead and get out your calculator and go into actually, we need to turn our stat plots off from our warm-up that we did. So hit stat. Oh, sorry. An easier way to do it, just go to y equals. And see where it says plot 1 is black right now? If you go up there and hit enter, it'll turn your scatter plot data off that we did for the warm-up today.
What if you didn't do it?
Well, then you don't need to do it.
And then clear out the y1 that we used for the warm-up, and let's graph 2 to the x power. Now, if you remember, this is actually the equation that many of you came up with when we were folding the paper. Remember doing that? 2 to the x power. So let's hit zoom. And since we were zoomed to our stat data, let's go ahead and go back to our standard zoom. And let's see what this looks like.
Zoom what? Zoom 10?
Zoom 6.
Hey, mine is saying quit.
It's pretty much on with you.
I didn't
So
know.
Is your plot 1? You're not following directions right now.
I don't know what it is.
I'm having a great day.
Okay.
You're bullying me.
So, what I want you to do is I want you to hit second table, and we're just going to use the table that it gives us for this.
Where's the table? Yeah.
So, it's above graph.
Well, I don't have that.
Where's the above? Oh.
I don't have that number.
Okay, the same quit.
You mean second graph? I was thinking table.
You just have to scroll up. You guys need to use your heads. I'm tired of answering dumb questions, and people that aren't, you just look at it once, you're like, oh, it doesn't match. Well, make it match. You just scroll up or down. Raina's not following directions. That's why yours isn't graphing. I already went over the reason that yours is getting errors.
Look at that.
Okay, so now I'm going to graph. I scrolled up to -4, and I'm going to graph -4, comma 0.0625.
Wow, that's gonna be fun.
So that's obviously very, very small, but just going to put a point right there. -3 is not much difference, 0.125.
These are the points that are on our graph, aren't they?
-2 is 0.25. -1 is finally half, like half of a block. -1, and then 0 is 1. 1 is 2. Now we're getting somewhere. 2 is 4. If you want to scroll down, you could see some more points.
What if
3 is 8. You could graph 3 as 8. And then obviously at that point we're up off of our 10 by 10 graph. Now what do you notice happens as I keep scrolling up? It gets smaller and smaller and smaller. And that means it's so infinitely small that they're typing it in scientific notation. That's 9.8 e to the negative 4. That means move the decimal spot 4 points to the left. Okay? So let's think of it this way. So what is happening as I move to the right? What is the rate? The rate is 2, right? So it goes from 4 to 8 to 16. It's doubling each time, right? So what's happening as I move to the left? Let's go backwards. What's happening if I move to the left? Half of it, half of it, half of it, half of it. Now what's going to happen if I keep taking half of something and half of something and half of something? Will it ever cross down below the x-axis?
No. You can only get to 0 because half is 0.
If you keep taking half of something and half of something and half of something, how much is always left?
Something.
Half, right?
Half.
So another way to think of it is, so there's the door into the hallway. If I get half as close, I'm right here, and I get half as close again, and then I get half as close, and then I get half as close, and then I get half as close. Will I ever actually get to the hallway?
I'm going to keep going.
And I get half as close.
No.
And I get half as close.
You're almost there.
How much is always left?
Half. But I'm saying, keep going.
So will I ever get out into the hallway? No. So this graph will actually never cross the x-axis, which leads us to a new term.
Oh, yes.
I want you to put a dotted line on the x-axis all the way across. Looks like that.
Mine's not red, though,
We'll learn more about it here in a second, but this line here has a crazy name. You might have heard it before. How do you think you say that? Asymptote. Yeah. You don't really say the P. Some teachers do. They're like asymptote. But everywhere I've always heard it, it's called the asymptote. The asymptote is a line that a graph approaches but can never touch or cross. It's basically like there's a force field right there. Because if you get half as close and half as close and half as close, it's never quite going to get to the x-axis as it moves to the left. Okay, so let's review a couple of the stuff we do every single essential standard. What would the domain of this exponential growth graph be? And you might want to make a note. This is called a growth. It's an exponential growth because from left to right, it is growing. Just like we read a book from left to right. So the domain would be what? All real numbers. Good. It goes left forever. Obviously, it's pointing straight left. And it's going to continue to grow to the right and up forever. But what about the range? It's not going to be all real numbers. Will it ever get below the red dotted line? No. So think, how would I write dotted line and up? Or really, it's just above the dotted line. Because it's never going to get to the dotted line. How would I write above the dotted line? And let's use parentheses and brackets, interval notation. Parenthesis. Where's the asymptote at? Y equals 0. Good. 0 to...
But it's not at 0. It's never at 0.
The asymptote is at 0. And what does the parenthesis mean? It's not going to get there.
Oh, I see.
So it's 0 to infinity, but we put a parenthesis on 0 to note that it's never going to touch the asymptote. Okay, where did this one cross the y-axis? Yeah, right at 1. So over 0, up 1. So let's write it as a coordinate point, over 0, up 1. And where does it cross the x-axis? It doesn't. So just write the word none. It's not going to cross the x-axis, okay? Now, I want you to do number 2 on your own. So graph at your calculator. I want you to go ahead and copy down some points out of your graph. So find some points that fit in the 10 by 10 window and copy those ones into your t-chart and then answer domain, range, y-intercept, x-intercept. So once you graph it, I would just go straight to the table. So second table, and then find, obviously I'm not graphing 131,000. So find a good section of the graph that you know will fit. So obviously I need to go up here. These are way too big. And you can see as I scroll down, they're getting much smaller. So they're... Now, why do you think my calculator is giving me fractions? Did you guys give you decimals or fractions? Did it do fractions? Did you use alpha y equals for the 1/4?
Yeah.
That's why. If I went back and I changed this 1/4 to 1 divided by 4, or even 0.25, so if I delete out my alpha y equals and then go to the table, see how it gives me decimals? So it gives you whatever you type in. If you type it in as an alpha y equals fraction, it's going to give you outputs in that same amount. So I'm just going to keep it as decimals for now. So then what I would do, if this was on my test,
Which one would you prefer?
I would just, it doesn't matter. I would just copy in the ones that fit into a 10 by 10 graph. So -1, 8 obviously is good. Over 0, up 2. Over 1, up 0.5 or 1/2. Over 2, up 0.125. And I usually do 5 points. That's what we did with quadratics too. So I would just do probably about 5 of them. Okay. And then on your graph, plot those values. -1, up 8. Over 0, up 2. Over 1, up 1/2. And then obviously what's going to happen as I continue to go down? Yeah, it's just getting infinitely small. Really, really tiny. But it's not, do you ever see it turning negative? No, they're always positive, okay? So it's basically doing the opposite of what we just did. So it's coming down, and then as we go to the right, it's half as big, or I should say a quarter, right? How do I know it's a quarter? The rate is 1/4. Okay. So now that you can see it, is this a growth or a decay? It's a decay. From left to right, this is going down. It's getting smaller and smaller and smaller. Okay, so let's answer our questions over here. What is the domain? All real numbers, left and right forever. What is the range? Yeah, it's the same, 0 to infinity. And really, it's best to always graph the asymptote. So let's get in that habit. Go ahead and put your dotted line along your x-axis. And then where did it cross the y-axis this time? Yeah, over 0, up 2. And there is no x-intercept. So that's how you would do this type of problem on the test. Okay. Last one, do example 3. Same concept. So if you're still working, that's okay. I have it graphed here. So you can see here's our exponential. It looks a little bit different. How does this one look different than the previous two? Yeah, this one went below the x-axis. Why do you think it was able to do that? Because the -3. So is the exponential itself negative? So this part right here, would that cause it to go negative? No, but the fact that there's a -3 out back takes the data and moves it. Where did it move? Down 3. Have we seen that before where the number out back moves something down or up? Yeah. And what do you think the +4 up in the exponent, what did this +4 do to it? That may not be quite as obvious. Typically, the exponential would be right here. But this one actually moved left 4 and down 3. So instead of having a y-intercept right here, what do you notice happened? Because it moved to the left, where's the y-intercept? It's like way higher, right? So it's not as easy to see as per se like a parabola, but it is there. It did move to the left a little bit, okay? I'm not too worried about that as long as you can come up with the table values. So if you scroll to -6, that's the one that I wanted you to copy down. So you just scroll up in your table and then copy down the values. You should have gotten -2.75, -2.5. I'm just copying this from the calculator. -2, -1, 1, and if you wanted to keep going, you could do -1 and 5. That would still fit on the graph. And then plot those values that your calculator tells you. So -6, -2.75, -5, -2.5, -4, -2. Did you all get these? -3, -1, -2, 1. And now what's going to start happening? It's going to start blowing up real fast, right? Where is the asymptote at? Where is the line that it's never going to cross? Yeah, and an easy way to tell this, like if on the test I asked you, like if I didn't tell you at all, I said, where is the asymptote? What I would do is graph it, look at the table, and scroll. What do you notice happens? What is it getting really close to? Not 3, -3. Do you see it? See how close it's getting? That's your clue that your calculator's telling you that there's an asymptote right there. I know it stops there. Your calculator basically gives up because see how there's no more room for decimals? Your calculator kind of just gives up. But that's literally telling you the answer. Your calculator's telling you that there's an asymptote at -3. Okay? So on your test, you have to graph the asymptote. So put a dotted line at -3, the y value of -3, and then connect your green points, which mine are green, so that it represents was this an exponential growth or a decay? Growth, because from left to right it was going upward. That's all you can do. That's as hard as the test will get for graphing. That's literally it. Okay? So on the back side, we learned about the asymptote. It is a line that the curve approaches. Now, for each of these, all I want you to say is it a growth or is it a decay? Okay? You can use your calculator. So go through and answer A, B, C, D. Is it a growth or is it a decay? Okay, A, growth or decay?
Decay.
Correct. Why do you think that is? Just looking at the equation. A fifth. A fifth of something, a fifth of something, a fifth of something is going to get smaller, right? What about B? Grow. Why do you think that is, looking at the equation? Yeah, the 4 is the base of the exponent. So 4 times 4 times 4 times 4 is the rate, okay? What about C? Once again, why do you think that is? Yeah, it's 1 point. If you multiply something by 1.2 an x number of exponential times, multiplying by 1.2 is going to do what? Increase it. What would cause it to decrease it? Not a negative, but a fraction. Think of it. Half of something, what's happening? Going down. Times 2 of something, times 2 of something is getting bigger. Now, D might have been the one that's not quite as obvious because you see the 3, you might expect that it to be a growth because of the 3, but the negative exponent actually does cause it to be a decay. Do you remember why? What does a negative exponent do to a number? So if we went back to last semester, let's say I had 3 to the negative first power. What does a negative exponent do to a number? Makes it a fraction. Remember, it moves it to the bottom of the fraction. So for example, 3 to the negative 1 is actually 1/3. So a third of something, a third of something, a third of something is in fact getting smaller. So the last thing for today, it says solving exponential equations with the same base. What do you think I mean by the same base, having the same base? Look at example A. What do you think I mean? The big number. The base of the exponent is what we call that. So, for example, if I had 2 to the x, what's the base? 2. A 2, okay? So we have this little, it's not really even a formula, it's just, this is kind of just common sense. If b to the m power equals b to the n power, so if the bases are the exact same, then what do we know about m and n?
They equal each other.
They have to be the same thing. That's the whole point of an equal sign, is saying that the left side is the exact same thing as the right side. So if we narrow it down and we know that the b's are the same, that means that the exponents have to be the same. So for like a real, even before this one, a really easy example. If I have 3 to the third power equals 3 to the x power. This is probably the most obvious equation you've ever seen. What does x have to be? 3, right? If the bases are the same, then that means the exponents have to be the same in order for the equal sign to be true. Does that make sense? So now let's take a look at example A. It says, solve the equation, basically knowing this knowledge. So if the 3's are already the exact same, what does that tell me about the exponents? They should also be the same. So what we can do here is we can take the exponents and set them equal to each other. So if I take 2x plus 1 and I set it equal to x plus 4, that's making the exponents equal, and we can now solve for the value of x that causes the exponents to be equal. So we get to get transported back to algebra 1 here for a second. So I'm going to subtract x over. That gives me 1x. And then if the x's are on the left, I'm going to subtract this 1 to the right. Therefore, what does x equal?
I knew it the whole time.
X equals 3. That's your answer. Now, to be sure, it's really easy to check. If we just take 3 and plug it in for the x's, what does the exponent on the left become? What's 2 times 3? Plus 1. So we get 3 to the 7th on the left side. And then on the right side, if we plug in 3 for this x, what does the exponent become? What's 3 plus 4? It's also 3 to the 7. So does 3 to the 7 equal 3 to the 7? Yeah, you don't even need to know what 3 to the 7 is. We know that they match. Okay, letter B. What's different about letter B than letter A? The bases aren't the same. That's exactly what I wanted you to say. So, what we can do is we can rewrite the equation. Sometimes, not always, but in this case you can. So what I mean by that, so 2 to the x plus 4, we know in order for this to work, what does the base have to be on the right side? 2. It also needs to be at 2. So what we can do is try and rewrite 64 as 2 to a power. You might have to check and guess a little bit, but it is possible. 2 to what power is 64?
6. So then x equals 2.
You guys figure it out? 2 to what power is 64? 6. Did I change the right side at all? No, I didn't change the equation. I just wrote it another way. It's like writing 0.5 as 1/2, right? I just wrote it another way. We know that 2 to the 6th power is 64. So now that the bases are the same, what can we do?
X plus 4.
Yeah, we take the exponents, and we know that they have to be equal to each other in order for this equation to work. In fact, you could probably just look at that and tell me what x needs to be. What does it need to be? Yeah, 2, but if you wanted to do the actual algebra here, we'd subtract the 4 over, and we get x equals 2. So in order for the left side to be the exact same as the right side, we would need x to be equal to 2. So if you're watching the video, go ahead and give C a go. It's very, very, very similar to example B that we just did. So you're probably done with C. It's not that hard. How could I rewrite 125 as an exponential with a base of 5?
5 to the 3rd.
Good, 5 to the 3rd power. Now sometimes, every once in a while, I'll get someone on the test that does this. What do you think is going through that person's mind?
They're crazy.
5 and 20.
What would I do?
That's a fairly, I mean, that's not an awful mistake. What do you think that they're thinking?
There's definitely D plus word.
They're thinking about multiplying 5 times 25. But are we multiplying here? No, we're raising something to an exponent. So be careful. Remember, it's at 5 times 5 times 5 is what we mean by 5 to the third. So then we take the exponents, we set them equal. What does x have to be? 9. Good. How many have you got 9? Good. C? Like a level 1.5.
That's exactly what I did.
Okay, last one, letter D. And just to not stress you out too much, let's go ahead and make this an equal sign. Let's just rewrite it as an equal sign. Now, we can't get the bases to match if something's on the bottom of a fraction and something is not. So, we do know, how could I bring this to the top of the fraction? Give it a negative exponent. So this could be 125 to the negative first exponent. So it's just like a negative exponent moves something to the bottom and becomes positive. If it's positive on the bottom, you can bring it to the top with a negative exponent, just reversing that step there. So now, typically we keep the smaller base. So what I mean by that is I would keep the 25. So 25 to the 2x. And I would see if I can rewrite the larger one with a smaller base. So real quick, see if you can do 25 to a power and get 125. So if we rewrite 125 to have a base of 25, what's the smallest whole number that we can do as an exponent? Well, we can do a 1, but obviously that doesn't work. So 25 to the second would be our next option, right? And that's way too big. We skipped over what we needed it to be. And otherwise, you can't write 125 with a base of 25. So, what we're going to do, we're going to make them both smaller. So I'm going to rewind here. What is a number as a base that can be written to a power and we could get 25 and 125 out of it? 5. So how could I rewrite 25 with a base of 5? 5 squared, right? But we can't forget about the 2x that was already up here. We're going to multiply those. So if something, we'll get to that in a second, but basically the 2 goes up and joins the 2x that was already there, okay? And then we have equals. How can I rewrite 125 as a base of 5? We actually just did it on example C. 5 to what power? 3. What was already up in the exponent to begin with? A negative 1. No, it's not. So what's the only thing that I did there? The 5s, let's see how 5 squared is 25, it's in green. 5 cubed is 125. The exponents that were already there just stayed there. So now, what does this become? What's 2 times 2x? 4x is all that happens there. Equals 5 to the negative 3. So therefore, if the bases are now the same, they're both 5s, we take the exponents, we set them equal to each other, so 4x equals negative 3. How would I solve for x if it's multiplied by 4? Divide both sides by 4. Therefore, x equals negative 3/4.